Hello everyone. Today I'm gonna talk about isolation forest and hopefully this helps you to get the idea behind isolation forest and how you can start using it quickly, especially in scikit-learn. If you're familiar with random forests, they would split observations based on random set of features in order to classify their observations to new classes or predict their continuous values in a regression problem. So we use them for classification or regression problems, which are uh, kind of supervised methods to solve the prediction problems. Similar to random forests, isolation forests randomly splits the observations, but the main goal is to determine which observation will be isolated first. So in this process of randomly splitting the data, we want to know which observation is going to be isolated first. Okay, let's start the random split maybe by this vertical line. Then probably next split is like this and it's in horizontal axis, or the second feature. And maybe the third random split is like this, and you see at this point this red point is already isolated. So number of split before isolation for this case is 3. So it takes 3 times in this case to isolate the red point. If you start this process from the scratch, and this time because you are doing again random split on random order of features, you may be lucky and you're gonna maybe split the point in 2 splits. And if you keep doing this, probably on average you're gonna get a number by 3. So on average it may take 3 times or 3 splits to isolate this point, this red point. Now let's look at the other case, when your red point is in the middle of the cluster and you start random splitting again. Maybe the first split is like this, second split is like this, and you keep doing this over and over, and obviously it's gonna take longer than the first example, and probably it's gonna take, say, 14 times, 14 splits to isolate this red point in the middle. And again, if you do the process from the scratch, you may get the number of 10. And if you keep doing this a lot of times, say 40, 50 times, on average maybe you're gonna get number 15, which shows on average it takes 15 times to isolate this red point. Now what is the meaning of these two numbers to us is, on average, the first example is going to be isolated much sooner than the second example. So the probability of being anomalous for the first observation or first example is much more than the second one. So second one is more probably is inlier, and the first one is outlier. You can read more about the theory of isolation forest in its reference paper. There are 2 of them here. The first one is the conference paper and the second one is a journal paper. But in this tutorial I'm gonna try to focus on scikit-learn way of implementing isolation forest and how you can use it in practical anomaly detection problems. Okay, let's get started. Right. First, I have imported a few libraries that we will be using in the following sections. NumPy, Pandas, Seaborn, Matplotlib, scikit-learn, in fact, isolation forest and min-max scalar from the scikit-learn. And next, we're going to import the dataset. We're going to have few datasets in this tutorial, and let's start with the first one. We're going to read this file, which is locally stored, and you're going to see in the GitHub or the link below. If we import this, and if we look at the head of this data frame, you're going to see there are two columns, and we can look at each columns individually, but let's first visualize them by plotting in scatter form. Let's convert the data frame to NumPy arrays, and this is mainly because scikit-learn likes the data to be in NumPy array format, not usually Pandas data frame. So let's convert them by using df.values, and if you run this, you're gonna see that you are having a two-dimensional NumPy array, and we can store them into a vector like x or a matrix like x, and you can look at the shape of this, which is 250 by 2, and of course the type of x now is NumPy array, but the type of df was Pandas data frame. Okay, and now we can plot them by using PLT. PLT is the Matplotlib pyplot library that we used and we imported at the beginning. So we can use plt.scatter, and we want to plot the first column of x, so the rows are not important, or all of the rows in fact, and the first, which is index 0, and all rows and second column. If we plot this, we're gonna see we have a data set like this, which has two clusters at a corner and some individual points around each. In order to train our predictive model, we're gonna use isolation forest predictor from the scikit-learn. I have the link here and you can Google it as well. If we click on that, you're gonna see it has, similar to other methods, it has different default parameters that you can change and you can set based on your problem that you're trying to solve. And important ones are number of estimators, which is basically number of trees or number of estimators that you are using, and their results are going to be ensembled, and they're going to give you the final anomaly scores and anomaly points, and maximum samples that you can set, contamination. This is one of the important ones that we want to set usually. And for example, if it is 0.1, it means you want to flag 10% of your observations as anomalous points. So you can set it from 0 to 0.5. And you can look at other features that you can set, but mainly we're going to talk about the contamination and how it overfits or underfits your data. Okay, so let's go back to our code and start writing some simple scripts. All right. So what we want to do is, first, let's use isolation forest that we already imported, right? Isolation forest. So we are kind of trying to classify things to normal versus abnormal. So we want to instantiate a classifier which is isolation forest, and we want to use the contamination as, let's say, 15%. Contamination equal to 0.15. And we want to fit our object with the data that we already converted from pandas data frame to NumPy array. And we want to predict the same data that we already fit, because isolation forest is unsupervised and we don't have a label for it. So we want to just learn from the data that we already have, which is X, and we want to see which of these X's are normal and abnormal. So we want to train or fit the data with X, and we want to predict also on the same X. Obviously, after you fit the data, you don't have to. For the future data, you may have X new, and you can use X new to predict. But for now, we want to just see for the whole data set that we have in this scatter plot, which ones are normal and which ones are abnormal. Okay, and if we plot this, or before plotting this, if you look at the numbers that are coming out of the prediction, you're going to have either ones or minus ones, which 1 shows normal point and minus 1 shows abnormal point. Since the output is NumPy array, we can use we can count the number of ones and minus ones. Say we can say predict, but before doing that, let's first save this as predictions, and let's use that predictions, which is NumPy array we know, and look at the ones which are greater than 0. If you run this, you're going to have a bunch of trues and falses, which shows, say, this is greater than 0. These are, we know for sure, the true ones are normal points because they are greater than 0, and the false is abnormal point. So because this is in binary format, true and false, you can add them together, or you can use mean method. Mean to count the number of ones and do the percentage. So this shows 85% almost. You have 85% normal in your predictions, and if you look at the negative ones, obviously you're gonna have almost 15% abnormal points, which is very close to what we already asked the isolation forest to flag as anomalous points. If you increase the contamination to say 25% and you fit and predict from the scratch, and now if you run this thing and if you count the number of anomalous points, you're gonna see that it flagged almost 25% of the points as anomalous points. But now let's do some more visualization to see which points are flagged as normal and abnormal points. To do that, we need the index of these predictions where we have -1s. So if we know that those indices, we can plot a red circle on top of these points and see which ones are flagged as abnormal points. So the first step is to grab those indices for abnormal points. To do that, NumPy has a where clause, which is very useful when you want to see where your predictions are, for example, negatives. If you run this for example shows the 4th observation, 5th, 21st, and so on. These are the indices that have been flagged as abnormal points. So if we store them in a vector called I don't know, anomalies, say abnormals, abnormal index. Now we can use this when we want to plot the abnormal points on top of these plots. So we can use the same thing again here and plot another one, but not all of these rows. We just want to plot these indexes. So abnormal indexes, I'm copying it. So we just want to plot where it is abnormal. And we can specify edge color too. Edge color, say red is usually indicative of abnormal point. Now if I plot this, it's gonna plot two figures on top of each other, but abnormal points, the ones we already collected from where clause, which was looking at the predictions which has values less than 0, we want to plot just those points with the red points. If we do that, you're going to see that these points have been flagged as anomalous points. Now let's change, this was with 25% of the contamination. So 25% of these points, the whole points, have been flagged as anomalous points. If we change it back to 10%, say, let's see which ones are gonna be flagged as anomalous. If we change this to 10% and fit the model again, and if we run this, we're gonna see that these points are not anomalous anymore. Okay, now let's look at another example, time series data. Uh, these are going to be readings from sensors. They could be any sensor, from sensors connected to a human body to sensors connected to equipment. The idea is that they are readings from some sensors. It could be 3, 4, 200, and these are collecting things over time. So time matters here as well. Um, all right, so I have the read CSV as usual. The file name is this, and the index column I'm going to decide to use time. If you look at the head of the data frame, it shows 3 sensors with different values, and it's over time. If you look at this index, it shows a nice formatted time, which they are apart 1 second. So that the sampling time is every second you have sampled, and you may not like this 1 second. You may like to do, say, a 1 minute average or 2 minute average. Pandas has easy way of doing it, and the only thing we need to make sure is the indices are in date time format. And to check that, we can simply look at type of the index. If you look at it, it shows index, which even we can look at the first item, and we're gonna make sure, okay, it is string. That's usually what happens when you read from a CSV file. Most of the datetime objects are gonna be imported or read as string objects. And if we wanna use all that beauty of time indexing, resampling, and many good things about time series data with pandas, we need to make sure we are converting these strings back to the date time, because without it, pandas is not recognizing what is the month or year or whatever inside this string is. So you cannot do resampling or averaging or parsing your dates effectively. Now, to convert this, we can use to-date time method from pandas. So pandas have a good method called to-date time, which you can use to convert this time index Now, if you look at this after conversion, the data type is date time. The only thing we need to do is to store it back to the index. So I'm going to copy this and use it as new index. If I run this, and obviously if I check my type again, it shows date time index, which is good, and we're gonna use it for resampling. Alright, similar to previous example, we can now convert the data frame, pandas data frame, to NumPy arrays using .values method, and define isolation forest as our classifier. This time we can even use fit predict method together. Just to save some space. If we do that, you're gonna see, again, we are gonna have some of the observations as -1 and some as 1s, but this time let's save these as predictions, and we're gonna look at another method called decision function. So after you fit this isolation forest, after you fit or fit predict, doesn't matter, you can use this method. This method is going to show you not just the binary or -1 and 1, it's going to show you continuous values, not just discrete 2 values. It's going to show you kind of like, we may call it, health of the system, and the idea is the more negative number you have, the more anomalous that observation could be, and the more positive number you have, it's going to be more towards normal cluster or class. So if we look at this decision function, obviously we need to enter the x. You're gonna see some positive and negative numbers. The best way to visualize this is to first store it in a vector, say decision function, and plot it with matplotlib. plt.plot decision function. Okay, if you plot this, you're gonna see you have some negative, some positive numbers, and the x-axis is observation number. Right now it's not in time format because this was just a NumPy array, and we didn't have the index, the time index that we already have. So we can, what we can do is to append this as a new column to our original data frame and then plot it. So our data frame was dfSense, sensor. Now let's add a new column called health, which is this vector that we just calculated, right? We got it from decision function method of the classifier. And now if you look at the dfSense head, you're gonna see this new column called health. We can normalize this later, but just to give you the idea of what's going on. Now we can again plot this new column that we just created, plt.plot, and you see the time, the x-axis now shows the date. So 4th month, the 1st of 4th month, and so on. It is smart enough to not show the year because it was only 2020. April, the month of April. Now we can even do some resampling, because you see it shows lots of spikes, and it is hard to interpret what is the meaning and how health behaves. Since the index of our data frame is already in date time format, this is going to be as simple as saying resample, say every 15 minutes, T for minutes. You can look at the documentation for more symbols, like what you can use for hour, month, or week, or whatever. And we want to look at the mean of these values every 15 minutes, right? So if I plot that, I'm gonna see much smoother graph if you compare it to the original one. Every second, every 15 minutes, you're gonna have much smoother because you are averaging the values every 15 minutes. And now you can set the threshold. Say we can flag any numbers below 0.03 as anomalous numbers or red zones. We can plot that with AXH span, which any number below or between 0 and 0.03 is gonna be colored with red. If you plot this, and you can go to a bit, say minus 0.5. So you got the idea. Any number below this threshold could be flagged as anomalous numbers, and obviously depending on the domain that you are working with, these thresholds can be different. It's not going to be hard if you know over time which threshold is going to show the healthy and unhealthy situation. There are some steps that we didn't cover in this tutorial, like if you look at these sensors, the data preparation could be important, since sensor 1 could be say temperature readings, and it is about 30-40 degrees Celsius, and sensor 2 could be vibration with very different range of numbers, and sensor 3 as well. So usually in machine learning methods, algorithms, they like to have numbers in similar ranges. That's why you can use libraries like min-max scalar, these library. But just to make it simple, we didn't put it in our pipeline, and you should consider it for your practical applications. All right, at the end, if you have any questions about any of these steps, please feel free to comment below, and I'm gonna get back to you soon. Thank you.